Hello everyone and welcome to the Do-It-Yourself or DIY Bioreactor Capstone presentation. The team includes myself, Tristan Chambers, and my two partners, Javion Rowland and Sam Oniha. So to start off, what is a bioreactor? A bioreactor is any manufactured device or system that supports a biologically active environment. In other words, a bioreactor is a vessel that is used to run a chemical process which then creates a biological substance. These substances are usually any sort of bacteria, with the most popular being E. coli. To have one of these bioreactors in your laboratory could range anywhere from $25,000 to $100,000. This large cost is due to the assembly of each individual hardware component being done for you, as well as the individual hardware pieces. A common and average sensor for a bioreactor is approximately $2,000. So if you think about all these different sensors, as well as mass flow controllers, as well as antifoamers, as well as pipes that need to be ran to run oxygen to the setup, your costs are going to continue to rise. And this doesn't even include software that is used to autonomously run the bioreactor process going on inside the vessel. And because these prices and this cost is so expensive, the average university does not have access to a bioreactor, which is now limiting their biochemical curriculum. So our goal is to reduce the cost of these setups so that more universities can have access to these bioreactors. The easiest way for us to reduce cost of this project is to find individual hardware and software components and assemble the bioreactor ourselves. We decided to choose the software first. For our software, we chose BlueViz. BlueViz actually allows a user to set up its bioreactor or fermenter to run the process on its own without user input. It also collects data from the process on its own when connected directly with other hardware. In a bioreactor process, the two most important variables to measure are pH and dissolved oxygen. We therefore decided to include two sensors to measure these properties in our model. When choosing sensors, we wanted to find options that would offer accurate readings as well as direct connectivity with BlueViz. In our search, we decided that the Hamilton EasyFirm Plus and Hamilton VisiFirm DO did these things the best. The specification for these sensors are shown below. So here's the pH sensor specifications. And here's the DO, or dissolved oxygen, sensor specifications. In order to get these sensors and other hardware components communicating with BlueViz, we needed to use Modbus Communication protocol. Within Modbus Communication are two main protocols, RS-232 and RS-485. RS-232 is used for slower communication and transfer speeds over a smaller distance, where RS-485 is opposite. It is used for faster transfer speed over longer distances. For our project, different hardware called for different protocols. For example, our two sensors utilize RS-485 software, whereas our mass flow controller and other hardware components utilize RS-232 protocol. In this picture, you can see our mass flow controller that utilizes an RS-232 protocol. And here you can see the RS-485 connector that will be attached to our sensors as seen here. On the left, you can see our vessel. And on the right, you can see the two sensors inserted in the vessel. The one on the right is the pH sensor, and the one on the left is the dissolved oxygen sensor. This picture on the left represents a top view of our bioreactor vessel, where each individual hole represents a slot for a sensor or any other hardware component to insert directly into the vessel. And this graph represents a successful BlueViz test run in which we tested deionized water and got a value of pH of 6 and a DO value, of 74%, which is average for deionized water. When thinking of more ways to reduce costs, we decided that moving away from BlueViz, which requires purchasing a license, would be a good option. We then decided to use Python, which is open source and free, to write a script that can collect data readings from USB Modbus scripts. We were able to write a script that found USB devices and their unique vendor and product IDs, as well as a script that outputs the power and bytes being used by the individual USB Modbus devices. These two scripts are a great starting point to the second phase of the DIY bioreactor project, which includes cutting costs even more. Even when using BlueViz, our estimated cost of assembly was approximately $6,000 to $7,000. This was considered a huge success in our efforts to cut costs and to make bioreactors more affordable and more accessible by the average university. But with a continued integration of Python and other open source components, more success can be achieved to revolutionize the future of biochemistry. We're happy to take your questions.